Hello, Mario! In this video, Mario's cul-de-sac 11, we're going to be looking at the roading details. In particular, we're going to be looking at the intersection and the cul-de-sac head. So what I've done is just taken my normal template and I've created two viewports to enable us to look very closely at the intersection and the cul-de-sac head. So firstly, let's have a look at the intersection. And what we have here, of course, is because the transitions around the curb returns at the intersection, because the road gets wider and it doesn't follow a consistent gradient in relation to the centre line, that we have to make sure that, one, we get the water flowing nicely around the curbs, and secondly, that we don't get large awkward transitions at the tangent points. So in this case here, we've got quite nice, gentle gradients, and they're all fairly similar, so there's no great differences in the gradient. So I'm fairly confident that we won't have any problems at the tangent points. In some cases, it may be necessary to look at the grade coming into the tangent point and the grade going out, and just to perhaps draw a long section through those just to see what's going on, as it may be necessary to transition from one to the other using some sort of horizontal curve. But in this case here, all I'm going to do is to calculate a level from the centre line at the known points or the tangent points, and then just evenly grade the curb around. That should be good enough. The curb layers usually will look at the smoothness of the curve when they're setting it out and make any smaller necessary adjustments. But for setting out purposes in this situation, that should be fine. Now we have the existing road up here, and the only information we have is the contour intervals, although we do know that it follows a consistent cross-section. So one of the first things I had to do was to calculate the RL at these points, and I did that just in much the same way as I did it here for the chainage 00, and that is I just worked out the distances from the contour below to the point to the contour above, and just did it by a ratio. So in this case here, I was able to get 26.856 tangent point left and 27.217 tangent point right. It's probably okay just to leave this recorded on a layer here that we can then turn off. So I'm now pretty much going to turn that layer off, which the layer that it was on is the cross-calc layer, this one here, so I'm going to turn that off. I'm also going to turn the contours off, the ground contours there and the ground contours major, turn those off. And so this is pretty much our diagram here, and as you can see, it's just done like that. Now I've just created a little tick point at the lip of each curb, just a little cross. I've created that as a block, and then I can just insert that. So having worked out what the gradient is, or the height is at these points, I just apply the 3% crossfall to get the gradient here. This gradient here, obviously at the tangent point, which is 18.45, the tangent point there, on the alignment, 18.45. Again, just go across for the 3% crossfall, 26.377 from 26.48, the design. That's the design alignment here, and the one on the other side of the road will be the same. However, when we're coming down through here, of course, it's going to be different on each side of the cul-de-sac because of the differences in gradient of the existing road. Now what I've done with the curb returns here at the intersection is just simply use the divide function to divide this arc into 1, 2, 3, 4 equal portions, and then I can just very simply just evenly apportion the difference in height. So essentially I've taken 27.114, 26.377, subtract one from the other, divide by 4, and that'll give me how much to take off each one. So then I'm starting with this one, take off that what I've worked out, round to here, so that's a nice even grade around through there, and that the water will flow around that curve. As you can see, it's going, the levels are falling there. Similarly on the other side, again, just dividing it into 4, so take the difference in height, divide it into 4, and progressively that would be subtracted from those ones there as it comes from there round to there. So you can see that you've got approximately 26.75, 26.377, around about 400 mils of fall around there, and similarly around here, 27.114, 26.377, significantly more fall around there, so the water will come around there. So that's pretty much it for the intersection, and just showing there, taking the opportunity to show little bits of information. Some of it's repeated on other parts of the plan, but that can be used to help people work out where they are. Now that brings us to, in another viewport here, the cul-de-sac head here, and just looking at that, I've got turned on there my calculation layer again. So putting a lot of the detail in there, straight away we can see that we can get our design height there, 29.534 at this one, and also our design height here, which is just on a consistent grade going up to there. Now using this one here, of course, we can come across here at 3%, which from our typical cross section to get our level at the Cuban channel here. And you'll see that one side is just a mirror of the other. And so in fact, I just sometimes use the mirror function to put these points across to here and then just adjust them so they're readable. Now the thing with the cul-de-sac head is that if we come from here and go across at 3% and across here at 3% and went out the back at 3% from this center point here, all of those points would be the same level, and it's not possible for the water to flow, and in fact it could well flow to the back here. What we're trying to do is get the water to flow out of the cul-de-sac. This means that we don't have to get stormwater reticulation right up here to pick up low points. The water can come here. We may only need to bring the stormwater reticulation to a point down here this far, which saves quite a lot of piping for the stormwater. So what I've done is I've just gone across here, from here to here, at what I believe is probably a minimum crossfall, which is minus 1.5%. So I've just gone from there across that, and then I've just graded everything easily back round to there. I have done a check to see what the percentage is, and we can see that across here that's minus 1.5, and so if I just take that grade there, 29.431, and this one across here, 29.934, and I'm just clicking on the arcs and adding up the arc length, I can see that I'm able to work out that I've got a grade of 1.583%, plus if it's going from this direction, which means the water will be falling down that way. So that's pretty good. That's sort of pretty much evened it out, and so that's what we're going to go with. So now it is a matter of just apportioning this around through here. Now what I've done is I've just taken this arc here and divided it in half. I've come across here at 90 degrees for these ones here, which is actually on the section line, and I've divided that part of the arc there in half and that part of there here and there in half. And then I have also taken this bit of arc around here and divided that in 3. Now what that means is that the distances between these points are a wee bit different, and so require a little bit of calculation. Now, how I've done that calculation is I've used my spreadsheet, my trusty spreadsheet. This is the same spreadsheet that we used for the alignment calculations, and we will come back to it again in subsequent calculations for the earthwork. So it sort of forms the a calculation type sheet for the job, which would go into the design report file and what have you. So what I've done here is, this is I've worked at a sort of a zero chainage around the curve at that zero at 29,431, and then I've added on 2 lots of 4.166, 2 lots of 4.189, and then 3 lots of 5.22. So they're the approximate distances around there, and there's 29,934, which gives me that there. Now, I just realised here that we could perhaps just calculate this here, just put a formula in there, and we'll just auto sum that there, and that's 32.37, which is the total distance around there. I did do a check to see what the total arc around through here by adding up these here and then doubling it just to make sure it all worked out. So yeah, I have, just make sure that you check that these totals do add up, otherwise you could get into some problems. So I have done that on here. Now, just putting those in there, I've got 29,431 there and 29,934 there. So I've just put in a formula here that you can see up here, obviously. And what that does is it just, for each distance, so it just takes the distance from 0, divides it by the total there, and then multiplies it by the difference in height, which it determines there, and then adds that on to the start value there, 29,431. So it does that for each one. So this is what I'm aiming for here. This is all calculated, so I check out that each one calculates. So that gives me my RLs around the curve. So 29,431, 29,496, 29,560, and all the way around like so. And then the right hand side is just a mirror image of the left hand side, and we can see there that we get the water going round. We have all these points, which will be a bit helpful later on when we come to do our earthworks and things, so we can see where our contours are going. I'm pretty sure I allowed for the -1.5% in my loan section, but if you showed it as a 3% grade, it is only pictorial, but you might want to just adjust that so that it is -1.5%, because it could affect the cut fill interface out at the end of the cul-de-sac there, which we'll be using for the earthworks plans later on. So let's just come back to here. So that's our cul-de-sac details. Mostly we should have sufficient detail on the roading plan for setting out the horizontal alignment of the cul-de-sac, but now that we have this information here, we can set out the vertical alignment of the cul-de-sac, and we're quite confident that the water is flowing out. So all that remains, just to tidy the plan up now, is to just go here and turn off the calculation layer, which is this cross-calc one here. So I'm just going to turn that off in this viewport. Oh, I got it right this time. Really good. And just spin back, and that's what our plan looks. Roading details. Our scale was 1 to 2,000, 1 to 200 at A3. So if you go into the models, you'll see I've got a 5:1 scale locked in there. My units are in meters. So 5 millimeters equals 1 meter, which is 1,000 millimeters. So that's 1 to 200. So there you are. That's our roading details plan.